So when you represent equation in aqueous solution, we use a little bit of a cheat, which is we write, this is what's called a molecular equation. Okay, so notice the soluble ionic compounds like the copper 2 nitrate, the sodium sulfide, and the copper 2 sulfide. They're written as if they're like molecular compounds. Sorry, the copper 2 sulfide is not soluble at all. It's got a solid there. The sodium nitrate is soluble, right? Anything with an AQ symbol, we write just like it's a molecular compound, like it doesn't break apart into pieces, but we know that's not accurate, okay? So for a molecular equation, we pretend soluble ionic compounds don't break apart, and we treat them like molecular compounds. Why does it matter? Well, it's easier to balance something like that. But we know this is not like a real representation of what's actually happening. So to get our net ionic equation, that is when we're going to split our ionic compounds, our soluble ionic compounds, I should say, soluble ionic compounds into their representative ions. And then if we have anything that's the same on both sides of the equation, we're going to cancel it out into ions. So you have to take into account stoichiometry, and you have to keep your state symbols. You can only cancel something if it is the same amount and the same state of matter. Okay, so there's an intermediate step where we're going to just break everything apart. So you could call that like the overall or complete ionic equation. So this copper 2 nitrate, we need to realize it's copper 2 plus AQ. And stoichiometry is important, so we have 2 of the nitrate anions, okay? And then the sodium sulfide, we have 2 sodium cations and sulfide S2 minus AQ. So that is all our reactant side. Then we have to look at the product side. So it's only things with the AQ symbol we're going to break apart. If there's a solid, if there's a liquid, if there's a gas, we're going to leave it exactly as written. Okay, so don't get slap happy and start breaking everything apart. Okay, CuS solid stays as it is, and then we have 2 sodium cations, AQ, and 2 nitrate anions. So just look what I've been doing here regarding the stoichiometry. If I've got 2 of the sodium nitrates, that means I've got 2 sodium ions, 2 nitrate ions. In the copper 2 nitrate, there's only 1 copper 2 nitrate, but within that there's 2 nitrate anions, so be careful. Okay, so then in order to write my net ionic equation, I'm going to cancel out any spectator ions. Okay, so I'm going to do this separately. So you can see that the nitrate appears on both sides stoichiometrically. There's 2 nitrates and they're in the same state of matter. Same with the sodium, there's 2 Na pluses. Okay, so to write my net ionic equation, it's Cu2 plus AQ reacts with the sulfide ion S2 minus AQ to form solid copper 2 sulfide. Okay, state symbols are important. So that is the only actual change that's happening. So that's why it's a net ionic equation, because it's showing you the only actual chemical change. Nitrate ions are there at the beginning, they're there at the end. Sodium ions are there at the beginning, they're there at the end. Nothing has actually happened to them in terms of a net change. So I'll do one more. Okay, so if there's an AQ symbol, you break it apart into ions. If it's a S solid, you leave it alone. Okay, so 2AgF AQ is going to be 2Ag plus AQ plus 2F minus AQ. Ammonium is NH4 plus, and there's 2 of them, NH4 plus AQ, and sulfide S2 minus AQ. And then our solid product is silver sulfide, and we have 2 ammonium cations and 2 fluoride anions in the ammonium fluoride. So hang on, that's the wrong kind of H. Ta-da-da. So you can see that you can cancel out the fluoride, you can cancel out the ammonium. So your net overall equation is that 2 silver plus cations combine with the sulfide anion to form the solid silver sulfide precipitate. And that's all you have to do.